Students, last time we have seen the Parkinson gear tester and the vernier tooth caliper. The next method to get the tooth thickness is base tangent method. This is a simple method in which we have to measure, as we have seen in Parkinson gear tester or vernier good vernier tooth caliper. We measure only one teeth at a time, the thickness of one teeth. Here the number of teeth depends upon the pressure angle and the uh, number of teeth, total number of teeth on the gear, and usually it is available from the design data book or the gear manual or handbook. So it can be seen that when we measure a single tooth, there can be the error, but if we measure multiple teeth, then the error can be reduced. So this base tangent method is used. Base tangent is the tangent to the base circle or the root circle. I have told you last time, the circle from the root of the teeth, that circle which is where from this teeth are say we are getting the teeth, so that root circle, the tangent to that root circle. So here we can see the micrometer is there, the two anvils are there, that two anvils are touching to this gear in such a way that they will touch at the root circle, and here the number of teeth taken are 4. So it is to be measured, that is to be measured with the help of this micrometer. So this is the actual reading which we are measuring directly with the help of this uh, tangent comparator, or we can say this gear tooth, this micrometer. And there is a theoretical formula also where we can see W is equals to Nm cos phi into bracket tan phi minus phi plus pi by 2n plus pi s by 2n. So where n is the number of teeth, m is the module, phi is the pressure angle, and s is the number of tooth spaces, where here the tooth spaces are 4. So 4 teeth are to be measured. So that will vary when we select the number of teeth. So with the help of this formula, we calculate the thickness, and we compare it with the thickness of the micrometer, means which we get it from the micrometer, and we can see the variation in between these two values, and we can see the error, so that we can compare with the help of theoretical calculation and the actual calculation. So whatever variations will be there will be the error. So this is what is base tangent method to check the teeth thickness, or we can say tooth thickness. Next is the tool maker's microscope. Tool maker microscope is a very simple, see, it is a sort of profile projector where we can see it is just similar as the usual microscope, the optical measuring machine equipped with the say screw threads, profiles, curvatures and angles. All this can be compared with the standard one, and we can see the errors in the eyepiece directly, eyepiece of the microscope. So toolmaker microscope is a type of multifunctional device that is primarily used for measuring tools and apparatus. These microscopes are widely used and commonly seen inside machine and tools, manufacturing industries and factories. So here there are two micrometers shown here. Thimbles are there with the help of which we can position the workpiece on this lens below this eyepiece, and we can adjust that with the help of the thimbles, and we can see the various things. As we can see, the determination of relative position of various points on workpiece for measuring the travel necessary to bring the second point in the position. So we can position that with the help of that two thimbles of the micrometers. Measurement of angle can be done which is done by the protector in the eyepiece itself. So in the eyepiece we can have that protector, and we can adjust the that setting, and we can measure the angle. We can compare the thread forms with the master profiles, which are again engraved in the eyepiece. We can measure the pitch, we can measure the effective diameter, and we can compare the enlarged or projected image, uh, which we can have on the projected screen. So this is the tool maker's microscope, under which we can inspect the gear profile, and we can compare its various parameters with the standard one, and we can find out the errors. So this is just a simple instrument, where just similar as the microscope. So just to see the various parameters of the gear teeth. Then next is the surface roughness measurement. Now here we have seen first the gear measurement, or the various parameters of the gears, and what are the available methods to measure the parameters of the gears. Next is the surface roughness. Now surface roughness is the whenever we are machining a surface, or when we are machined a surface, then there that surface is having certain roughness, and that texture is to be inspected and to be seen whenever it is the part of a which is going to assemble somewhere, which is having very sophisticated type of instrument, in which the surface is going to assemble with some other part. So while doing so, we have to inspect or check the surface roughness whenever we are carrying out certain manufacturing process. So surface roughness is nothing but we calculate it in the form of RA value. RA, or it is also known as CLA. CLA is center line average, the same. So it is the arithmetic average deviation of the surface valleys and peaks. Now expressed in micrometers or micro inches or microns, we can say. So here this diagram we can see it is a specimen shown here, where we can see the lines. These lines are nothing but the primary roughness, which are the peaks and the valleys. Peaks means the extended part, and valley means the root, or we can say the uh, deeper part after that crest, or we can say the peak. So peaks and valleys, all this is what the primary roughness. Then we have seen the waviness in the surface. So this waviness is nothing but the secondary roughness. So these are two things. This roughness depends on various factors. These factors are the types of coolant used, then the cutting parameters such as feed, speed, depth of cut. So if it is having certain, that machine is having certain vibrations, we are cutting it at very high speed, so many things related. If whatever we are machining, we are carrying out, if it is not in the ideal condition, then that will create certain type of roughness. So cutting parameters such as feed, depth of cut, then the type of machining which we are doing, rigidity of the system consists of machine tool, means whether it is robust or rigid or not, whether it is having certain vibrations. Then the fixture which we are using to fix the workpiece with respect to the machine. Then cutting tool, if the tool is blunt, is not say we have restored all the angles on the tool geometry is disturbed, then that time also we can have the roughness. The workpiece itself will create the material of the workpiece can create the roughness. Vibrations is one of the major factor, material of the tool and the workpiece. So these are the very common factors which is affecting the surface roughness. So these are the two types of say roughness, that is the primary roughness and secondary roughness. So it is in the form of primary roughness is in the form of peaks and valleys, and the it shows the lay direction. This black line here is showing the lay direction. It is like this, parallel to the these lines with peaks. Then this is waviness spacing, the space between the two waves. So this is the height of wave. Then this is the roughness width and roughness height. It is shown with the help of this spot. So this is the overall idea about the roughness in the part. So it cannot be seen with naked eyes because it is very finely machined, but still this roughness is there in the workpiece. So this is shown the average vertical deviation. This is the center line, and this is the sampling length. It is the length of the sample, and we can see the peaks and valleys. This is valley, this is peak. So this is vertical deviation, this is actual surface, nominal surface. Nominal means the baseline. Along this the peaks and valleys are there. So if we take mean of this, see here the area shown above this baseline or the mean line or the center line. Below that, so peak and valley. So we can have this area and it will different every time. So if whatever sample we have chosen, here we can see the center line average or CLA method. So this CLA value we can calculate with the help of this. So here it can be the height of the peak and the depth of the alternate peak. So H1, H2, H3, H plus up to Hn divided by n, the number of the heights, is known as CLA value. Or it can be the area under that peak. So it is A1, A2, area under peak or area under the valley. So these areas can be added divided by the length, that is the specimen length, can be again CLA value. So you can calculate the CLA value here. So surface roughness is measured as the average deviation from the nominal surface. So nominal surface is the base surface or the center line. So everything above it and below it, means the peak and the value, is nothing but the surface roughness. So it is the average value of the ordinate from mean line regardless of the arithmetic sign of the ordinates. Means it can be peak and it can be valley. Both time we have to add. So A1, A2, A3, A4, A5 up to AN upon the length, sampling length, is nothing but the CLA value or the RA value. This is the machining symbol, which is a standard roughness indication symbol. So it is a inverted triangle shown with a extended line and a horizontal line. So this type of symbol we use to designate the roughness. So here the machining allowance in mm is shown. Then the roughness value RA is shown in microns, and it gives you the grade symbol up to N1 to N2. So N1 is a fine roughness, and as it goes from N2, N3, N4, N5 up to N12, then the roughness grade is increasing. So that is designated in the design data book depending on the RA value. As you can see, for N1 it can be 0.05 micron, and if it is going on, for example, if it is going on increasing, then the grade is changing from N1 to N2, N2 to N3. So this all these roughness values are tabulated, and for some roughness values, first roughness values, the grade is given as N1, and then it goes on increasing the grade. So grade symbol N1, N2, N3 can be mentioned here above this triangle. So that gives you roughly the idea about what type of roughness we are having in that workpiece. Then production method or the treatment or the coating, whatever the last operation we have done on that workpiece on that surface, what is the last operation? Whether it can be a machining operation or it's a finishing operation or a coating operation a spraying operation, whatever last operation we have done, that will be mentioned at B. Then the sampling length in mm and the direction of lay. So how the lays are there, that we have seen here in this sample. This is lay direction. So this lay direction will be also mentioned here in this symbol. So from this symbol we can get the overall idea about the roughness or the surface which we are having in the workpiece. So that is India. Now here we can see the various lays, standard say parallel symbol. If it is like this, then it shows that the lays are parallel to each other. Then the perpendicular one crosswise, so it is the direction of lay which say perpendicular, so it is nothing but such type of symbol. Then if it is cross, diagonal lines are two diagonal lines are drawn like this, then it is multi-directional, so symbol is like this. If it is concentric, it is symbol is like this. And if it is say uh, centered at some point, then it can be like this. So these are the types of lays and their symbols. So they are indicated as parallel sign, perpendicular, then this cross, then m is multi-directional, c is concentric, and rough is rough means the it is centered at some point and it is having some rough surface. So r is there. So these are what the lays, direction of lays. Then next is this Tomlinson surface tester, where from we can test the surface and we can draw the profile with the help of the pointer. So it is just simple mechanical type of instrument which is used to test the surface. It is Tomlinson surface tester. So there is a probe here. This stylus is there with which is attached to a diamond probe. So this tip is made up of diamond and it is mechanically connected through this spraying to this horizontal motion of the body and to this arm, which the arm is fixed to this body, and it is with the help of this roller it is connected to this stylus also. So as this diamond probe moves along this surface of the workpiece which is to be tested, then this graph we can plot, or we can get the reading of this surface. We can just get the profile of this surface and we can get the roughness value. So there is a skid before this diamond probe. First this skid is moving and then this diamond probe is moving, as you can see in this diagram. As this diamond probe is very precise, costly, and it should not get affected with the roughness. So this is a pilot which will move further first and then this diamond probe is moving. So this is skid and then this stylus is moving behind it. So to get the roughness of the surface, and this is converted through this mechanical means into the moment of the pointer, and we can get it on the we can get in the form of a graph. So we can get this through the mechanical means directly. So this is Tomlinson surface tester. The working is given here. You can write this and we can get it on the smoked glass and we can get the profile of that. Then the Taylor-Hobson surface roughness meter, that is TallySurf it is known as. This is a electrical type of surface roughness meter where this armature is there and this resistance, this armature is connected to directly this stylus. This stylus is moving on the roughness. See this. As this stylus moves on this surface, this will move this armature up and down. So if this armature is getting connected with some resistance, that will get this bridge is there, that will get disturbed, and because of that there will be generation of the uh, say this value, or we can get it in on the meter. We can get some value on the meter, and we can directly plot that reading in the form of a graph. So as this stylus, which is coming in contact with the surface roughness, then this armature will tilt by some degrees up or down. It will disturb the resistance in this one of the element of this bridge, and that will differ, that will make changes in the reading on the meter, and we can plot the graph in the recorder. So we can get that. So this is the carrier graph as it is shown in below. This is the graph produced by the so this is the carrier graph, which we get it from the this standard graph from this Talisurf indicator. Then this is modulated one. In the second slide it is shown, which we are getting the as a reading. Now this is the graph which we are getting as reading. This is the graph or the pattern shown by the instrument itself. From this is subtracted, or we can say we further magnify this, or we further amplify this, subtracting this graph by the instrument, and we get it demodulated graph like this. So this is the graph of the machine original graph. Then this is modulated graph. This we I got it from the surface roughness. This is demodulated by subtracting this carrier graph, and then we get the final reading or final profile of the roughness. So this is Talisurf Taylor-Hobson surface roughness meter, which is used to an electronic instrument or electrical instrument, which is used to get the surface roughness. So this is the description given here. Then next is mechanical roughness indicator, that is Maccarin, it is also known as. So this particular is nothing but a mechanical type of trigger gun, where the shape of this is shown here. So this is the mechanical roughness indicator. It is also known as Maccarin. It is having a dial here, where the grade of the roughness N1, N2, N3, N4 is given along this dial, and there is a pointer. Then this is a gun size type structure. This is the operating trigger, and above this surface there is a blade here, very flexible and very fine blade is there. That blade is further extended up to the left corner of this dial, this particular Maccarin, or we can say roughness indicator. So it is extended at the tip also. So some part of that blade is coming out of this indicator at this corner. This blade is having a cover which is made up of glass, and we can visualize that blade from this glass cover. So as we want to compare the surface roughness, or we want to get the RA value of this surface, we've set it at an angle, say initial angle may be say 15 degrees or 10 degrees. So it is in this diagram, it is shown, just for example, it is shown as 15 degrees. So at 15 degrees, we will move that tongue, or that particular blade which is coming out of this, we will move that tongue along this surface roughness or surface sample length, and we can see the reading. If the pointer is not moving, then we go on increasing the angle. So we are making it say 20 degrees. Then still we are not having the reading, then we are making it again increasing, so say 30 degrees. So we go on increasing this angle. As this angle, it is hold in hand, as we are increasing the angle, at some angle we can find the movement of the pointer along this scale, where from it will indicate some symbol, or it will indicate some grade N1, N2, N3, N4 like this, and we can see the with respect to that grade we can see the array value at that particular. So this angle which we are changing all the time, for first moment it is not, say, at 10 degrees it is not showing any reading, then second moment at 20 degrees, third moment at 30 degrees, fourth moment is at 40 degrees. So we are going on changing the angle of this particular indicator with respect to this surface of the workpiece. That angle is known as angle of attack. So that angle of attack, if we go on increasing, then we can see the buckling of that blade. As you can see here in this cover, it is shown buckling of this blade. So as it is getting buckled, it means that the surface is somewhere it is having some problem, and it will also show, the indicator will also indicate some value, some grade value along this dial. So it is a simple mechanical type of uh, indicator which indicates the roughness grade of that particular workpiece with the help of the blade which is moving along this surface. So that is a tongue like blade, very flexible, very smooth. It is moving along this surface, and if it is getting buckled at some angle, so the number of times we are moving it on this, so at, and by changing angles, say 10, 20, 30, at some point we can see the buckle and we can get the indication of the grade value at that point at the surface. So this is just simple mechanical roughness indicator. It is also known as shortly Macarin. So this is the description given. The incorporates a pendulum or gear mechanism and the buckling blade observed through the transparent cover. The dial is calibrated in terms of N grades and the corresponding central array values. So N1, N2, N3 depending on the array values. And this nothing but when the blade get buckled, we get the reading in the dial indicator. So this is what is the surface roughness indicator, mechanical type of gun type structure. With the help of we get the surface roughness grades. So this is what is this. Then next time we'll see the flatness checking with the help of optical flat, and the CMM, the last one, that is coordinate measuring machine. So this we'll see in the next video. Thank you.